Hi all, we are into a new module today, our fifth module. From here on, we are getting into electromagnetic waves or time varying field, both electrical and magnetic. Basically, this fifth and sixth module, they are just like continuation about electromagnetic waves. So we are getting into starting from our Maxwell's equation and getting into the electromagnetic waves. Uh, that is what we are going to do today. Okay, so till last class we have seen about different conditions and in module 4 this module what it covers is like this. Basically it is about electromagnetic waves. So first we will be deriving our wave equation, means electromagnetic wave equation from the Maxwell's equation. Then we will see what is uniform plane wave. We will also derive wave equation in phasor form also. So means we are starting to formulate electromagnetic waves. So that is our first part of this module. The second part of the module includes some concepts on Poynting vector and Poynting theorem, power flow in a coaxial cable, and complex averaging Poynting vector. Means basically it is about power. Okay, we are going to see power in terms of this electromagnetic wave propagation. So that is our that are the contents of our fifth module. By going through this all, we are getting in our objective is that the course objectives of this module are this, means from it is basically applicable for the coming two modules. What are the course objectives? To understand the relation between the field and the time varying conditions, right? That is some of that is covered in the last module also. Then the second part is that to understand the principle of propagation of uniform plane waves. So we are going to see what is meant by uniform plane waves and all. So these are the two course objectives that we are trying to achieve by going through this particular module. Let us start from Maxwell's equations. This is the general form of Maxwell's equation. Before the before lockdown, we already have derived a similar table we discussed in our class for static fields, right? It was for what? It was for static fields. Now here this is the you can say this is the general Maxwell's equation. We will just discuss about this. Del dot D equal to rho V means what? It is about the Gauss's law in electrostatics, right? So where it will remain the same whether it is electrostatics or it is time varying. There is no change for this equation. Maxwell's equation, as we know, we usually represent it in two ways. One is the differential form, another one is the integral form. So in differential form, what is the difference between differential form and integral form? Differential form we also call as point form also, because when you see the differential form equation, del dot D equal to rho V, del dot B equal to 0, or del cross E equal to minus W, all those equations, they are defined at a particular point, right? We can define the flux density at a particular point, right? And that is why these are called as what? Point form. Okay. Integral form usually is for a particular surface or particular volume or a particular loop. So it is different. It is defined that way. So this differential form, that is the main difference between the differential and integral form. Differential form is also called as point form. And basically the differential form we usually use to solve field in a particular domain. Because when you know as I already said, it is about a particular point. What is the flux density at a particular point, or what is the magnetic field flux density at a particular point? These things can be well communicated with this differential form. So that is what we use to solve the electromagnetic field at a particular in space. But in the integral form, they usually tells us what are the physical laws or what are the phenomena. Very clearly they will tell us. So that is the importance of the integral form. Okay. So now our first law is what? The Gauss's law. that remains the same whether we are getting into static condition or the time varying condition. Similarly, del dot b equal to 0, right? Here del dot b equal to rho v, because when you take a particular closed surface or a particular closed surface, there you can say what there will be some if we keep a charge, we can keep a single charge there, and there will be a flux density, okay, and it is diverging. But when you take the case of a del dot b, or when you take the same closed surface for a magnetic field, then the existence of magnetic monopole will not be there. Because of that, whatever flux is going through going out from one surface, the other way that same flux will be coming in also. That is why we get del dot b equal to 0. So that concept we discussed. That is about the non-existence of magnetic poles. And these two equations, del dot d equal to rho v and del dot b equal to 0. These two equations are valid always. These equations are valid always, whether it is static or time varying. There is no change in these equations. And for the other two equations, when we considered static condition, del cross E was 0, or we call the electrostatic field as conservative. Afterwards, while introducing Faraday's law, we understood that the del cross E is what? Minus dou B by dou T, or that is not conservative. There is a curl associated with our field. So that concept we discussed in the last lecture, right? So this del cross E equal to minus dou B by dou T, that there is a modification occurred compared to what? Compared to our static condition. And its integral form is easy to write, right? So before our E dot dl was equal to 0. Over the closed loop, E dot dl was equal to 0. Now it is equal to what? The same only, minus dou by dou T of, means it is integral over the surface, minus dou by dou T b dot ds, right? So that way we will get the integral form. It's just whatever equation we got here, the same only is put in integral form here. That is about Faraday's law. Now before this, del cross H was only equal to what? J in our magnetostatic condition, but we introduced the displacement current in our ambient circuital law. So this particular displacement current component, that is the major contribution of Maxwell. Means when Maxwell was formulating Maxwell's equations, it is quite mathematical. So that time all other laws are known, but the existence of this displacement current was not at all known also. So he proposed that first, and afterwards Heinrich Hertz came and he verified that experimentally. So that was the major contribution of Maxwell, the introduction of displacement current. So another interesting part with our time varying case is that before time varying, when it was static, as you can see, this first two equations are applicable for static also. Del dot d equal to rho v, means there is the terms are only related to what? Terms are only related to the electric field only, right? D is electric flux density, rho v is what? The volume charge density. This is about the electric field only. When we take del dot b equal to 0, again the same thing happens. But in del dot b equal to 0 also, what is this del dot b equal to 0? There also only the magnetic field parameters are there, like magnetic flux density B, right? Right, but when you come to the time varying field, it is changing. When you come to the time varying field, what is the change? Del cross E equal to minus dou B dot T. Here your electric field is in the left hand side, and what your dou B by dot T is in the right hand side, right? Electric field is in the left hand and dou B by dot T is in the right hand. So they are related, or they are coupled. When you are coming to time varying field, time varying electromagnetic field, then what we can say, these both are coupled, or they exist together. So that is the main concept in what? Electromagnetics, or the time varying field. Similarly, here also you can see this is the magnetic field intensity H, and you have got your what? Electric flux density variation dou D by dot T on the other side. So here also again what? Magnetic field and electric field are related, interrelated, right? So that is the main change when we come to the time varying field. Your electric and magnetic field are coupled, or they are interrelated. So that is the concept in time varying field. Okay, when you have a charge, it can produce electric field, right? When it starts moving at a constant velocity, we call it as current, and that can produce what? Steady magnetic field. This much is what about the static condition. Your charge is at rest, it is electrostatics. Your charge is moving, but still what? It is moving at a constant velocity, that which produces current. That is magnetostatics. When we come to time varying field, either your electric field is changing or your magnetic field is changing. Then they start changing together. Like I have a conductor. I have an AC conductor which is carrying some 50 hertz AC. Okay, I have an AC conductor which is carrying some 50 hertz AC. So the current in this conductor, that is varying sinusoidally with respect to time, right? So the current in the conductor is varying sinusoidally with respect to time. So here at a particular point, as I am marking here, whenever this current is passing, at this point, at every instant of time, what will happen? The magnetic field density B also will change, similar to the way your alternating current is varying here, right? So this alternating current or whatever we apply here, that is producing electric field, or we can say that this magnetic field is varying, similar to what your electric field is varying, right? So or at this particular point, your both the magnetic field and electric field are varying. Am I right? When you have a constant, when you have a constant supply of current, your electric field will be constant at this point, right? Because the same amount of charge is flowing all the time, so you can say the same electric field will be applied. As we have seen across a conductor, if we apply some potential, the electric field will be what? The constant. So here that electric field will be constant. Once it is varying, your electric field also is varying at this point. Same time magnetic field also is varying. So and they both affect each other also, right? Like if you consider an alternator, inside alternator or means dynamo, when you start rotating your coil in the magnetic field, then what? Induced EMF will be produced. That much is okay, that is Faraday's law, right? Induced EMF is produced. Once your induced EMF is produced, then what will happen? Through that loop a current will be flowing. That current will be what? That current will change with respect to the flux it is cutting, right? So that current will be what? A time varying current. Whenever the time varying current is happening in the loop, again that will produce what? A magnetic field which will interact with the field, already excessive field. Means these two things happen, magnetic and electric field, they happen simultaneously. So that condition we call as was electromagnetic field, or the time varying field. Okay, and at this point, at any point in space, already if at all you have a constant current also, magnetic or electric field is what? Varying in space. At every point it will be different. Once it is time varying also, at every point in space it is also varying with respect to time also. So now our field is varying with respect to space as well as time. Okay, that is the concept of a wave also. So that we will cover in the next lecture. Now let us just get mathematically into our electromagnetics. So these are the four equations. The last one, two, the curl equation. Now in the Maxwell's equation final form, the first two equations, you can say whenever you come to time varying field, your divergence remains the same, right? Del dot D equal to rho V or del dot B, if you take, both of them remain same. So divergence remains the same. What is the changing is what? The change is happening for the curl. You can say the curl is getting modified. As for the last two equations, del cross E become what? Minus dot V by dt, and del cross H become what? J plus dot D by dt. There is an increase in there is a increment here by displacement current. So there the curl is getting modified. So I just want to conclude this Maxwell's equation in general form. For a field to qualify as electromagnetic field, it should satisfy the all four Maxwell's equations. Understood? They are Maxwell's equations are mathematical, and whenever you say it's an electromagnetic field, then these four equations should be valid. That is the importance of these equations. Okay, and it summarizes all the known laws in electromagnetics. Right. So that is the importance of Maxwell's equation, or that is how we are using this Maxwell's equation to analyze electromagnetic field, and it is the basis for electromagnetic waves, as we will see from here. Because electromagnetic waves means what? Something which is varying with respect to time and space. Okay. So when we consider time varying field, that already takes in what? Electromagnetic waves. Now, let us get into derivation of the wave equations. We have seen the we know now we are getting into the time varying potential. We already defined the potentials for what? The static conditions. So the scalar electric potential, right? The scalar electric potential, whatever we know the potential difference, that is given by what? Rho v dv by 4 pi epsilon r integral over the volume, right? So this we already know. The scalar potential is given by rho v dv by 4 pi epsilon r, right? Right. So a particular for a particular volume, if we know the volume charge density, then at a particular point r, we know that it is given by what? Rho v dv by 4 pi epsilon r. This is known. So similarly, in the third module we defined magnetic vector potential. I think it was one of the last lectures in the third module. We defined it as what? The vector A is as also as mu j dv divided by 4 pi r. I hope you remember. Okay, you can go back and see if you want. A vector A, that is the magnetic vector potential. Okay, we also discussed about why it is needed to define such a quantity, so that we can write as mu j dv by 4 pi r. Okay. Now what we are going to see is that what will happen when the fields are time varying. Okay, what will happen when the fields are time varying? I hope you remember that the vector A, magnetic vector potential, this is a vector potential and this is what? A scalar potential, right? Magnetic vector potential A, that is defined based on what? Del dot B equal to 0. We already know that del dot B is 0 where del dot B equal to 0 for the case of what? For the case of time varying field also. And when this del dot B equal to 0, we can define B as del cross A. Right, we can define B as del cross A, because del cross A, the curl of the divergence of the curl of any vector is equal to 0. So based on that only we are defining what? The vector A, which is magnetic vector potential. So del dot B equal to 0, based on that we are defining vector A. Okay. And the definition is this, what? B equal to del cross A. Okay, that is the definition of A vector. That is how we are defining what? The magnetic vector potential. Faraday's law is given by what? Faraday's law is given by del cross E equal to minus dou B by dot T, non T. Okay, so here we have got what? We have got the magnetic flux density B here. So if we apply B equal to del cross A here to introduce the magnetic vector potential, what we will get? We will get del cross E equal to, in terms of, in the place of B, we are going to apply what? Del cross A. Okay, so del cross E equal to minus dou by dot T del cross A, right? So that we get, applying this B, we get the minus del cross equal to minus dou by dot T of del cross A. So if we see that, and we can take this the right hand side to the left hand side, so it will become what? Del cross E plus dou by dot T of del cross A equal to 0, right? So and as you can see here, this dou by dot T here, dou by dot T and del means what? Dou by dou x into ax cap plus dou by dou y into ay cap plus dou by dou z into az cap. That and the dou by dot T means what? This is the differentiation with respect to time. These both are these both are independent. They don't have any, not related. So we can take it inside or outside as per our wish. So that this equation we can change as what? Del we can take out as common. So del cross E plus dou A by dot T equal to 0. Right? Del cross E plus dou A by dot T will be equal to 0. Okay, so now the interesting thing what we are going to do here is that the same thing here also we can write as what? Some curl of something which is equal to 0. So the curl of the gradient. So we can write as what? The curl of the gradient, because del cross minus del v. The curl of what? Curl of divergence of a vector. Del cross minus del V, that can be created as what? 0. So that we will apply here. That what on the right hand side, del cross minus del V we will apply. It means what? What we will get from there? Curl of one vector here, curl of what another thing here. So this E plus dou A by dot T, that will become equal to the negative gradient of potential. That we can write here like this. So E plus dou A by dot T in time varying field, it will become what? Equal to the negative gradient of potential. Electric field plus the magnetic vector potentials change with respect to time, right? So that is equated as minus del V here. Now same after rearranging, we will get electric field as what? Minus del V minus dou A by dot T. Interestingly, what it have become? The electric field intensity has is written in terms of what? The electrostatic scalar potential and the magnetic vector potential. In terms of that, we have written the electric field intensity here, right? This is an important part. Now another equation valid. This is from where? This is from where our del dot B equal to 0, that we are introducing what? Vector A. Now another equation valid for time varying field also is what? Del dot D equal to rho V, our Gauss's law, right? So when del dot D equal to rho V, we can write D means what? D equal to epsilon E. So we can write del dot E equal to what? Del dot here it will become del dot epsilon E. So that is equal to rho V, or del dot E will become rho V divided by epsilon, because we are taking it to the other side, right? Rho V divided by epsilon. That electric field intensity E here, that we already got here, what? Minus del V minus dou E by dot T for time varying field. So we can apply that here. That will become del dot what? In terms of electric field, we will write minus del V minus dou A by dot T. Okay. So now this rho V by epsilon, we are taking out this part, we are concentrating on the other part. Rho V by epsilon will become what? Rho V by epsilon will become minus del square V minus dou by dot T of del dot A. Means what? Del dot minus del V. No? This will, when we take this thing inside, it will become what? Minus del square V. And when we take this del to this side, that is what is written as here what? As I already said, dou by dot T and del are what? Independent operations. So we can take it inside also. So that minus del square V is the first term that we already discussed. Second term will be what? Minus dou by dot T of del dot A. Minus dou by dot T of del dot A. So that is the that is what we get from here. Once we rearrange this, what we will get? If we just rearrange it, we will get it as what? Del square V plus dou by dot T of del dot A equal to minus rho V by epsilon. So here what we are our equation is quite free from what? The electric field density or the magnetic field density, right? Just like our Poisson's equations or Laplace equation, del square V equal to what? Minus rho V by epsilon, which we use for finding out the, which we can use for finding out the field. We discussed long before. Similarly here also we are only dealing with the potentials. One is the static scalar potential, another one is the magnetic vector potential. So and there is no field coming in. So that is one good thing here. So this equation is one of our bases, del square V plus dou by dot T of del dot A equal to minus rho V by epsilon. Okay. Now let us take consider the another equation. What is that? We already defined B equal to del cross A. I hope you remember. So if you take the curl of that equation, means what? Del cross A. Right, del cross B, del cross A means what? Del cross A is there. Okay. So if you take the curl of that equation, then what it will be? Del cross A, or it is what? Del cross B is. Okay. B, the magnetic field density, we can write in terms of magnetic field intensity. What? The B equal to mu h. So we can change it as del cross mu h. I think there is no doubt on this. B is del cross A. If we take the curl of del cross A, what it will become? Del cross B. So that will be also equal to del cross mu h. So these two equations, this we defined in the last slide, or the slide before, equal to what? Minus dou V minus dou A by dot T. I already told you that this is important. So You should remember this, E equal to minus dou V by dou A dou t. And another equation is our fourth Maxwell's equation on ambient circular law, del cross H equal to J plus dou D by dou t. We are going to use these two equations here. How? The equation here, del cross mu H, we can write as what? Since mu is a constant for linear isotropic materials, so we will take out this mu into what? Del cross H equal to what? Mu into del cross H, right? This will become mu into del cross H. And we already defined what we already defined. We already defined what it is equal to mu J plus H is equal to what? J plus dou D by dou t. So we are defining it as mu equal to mu into J plus dou D by dou t, right? Now what we are going to do? Now mu into del cross H will be equal to mu into J plus dou D by dou t. D we are replacing it with epsilon E. Right, D equal to what? D is related to electric field intensity by what? D equal to epsilon E. So this will become J plus dou epsilon E divided by dou T. Now we will take the mu inside the bracket, so it will become mu J, the first term, plus what? There is an epsilon inside. Again it is constant, so we can take the epsilon out also. So that will give you mu epsilon into dou by dou T of the remaining part is what? Electric field density. That electric field density we will give the equation of for time varying field, which is minus del V minus dou A by dou T. So that is what we are giving here. We are applying two equations here, okay, and the conditions that B equal to mu H and D equal to epsilon E. Right, B equal to mu H and D equal to epsilon E is known to you. Apart from that, we are also using what? The two equations. One we derived just now, and the other one is what? The Maxwell's equation is del cross H equal to J plus dou D by dou T. So this way we get our equation that what as what? It is equal to mu again if we take this thing mu epsilon inside. First part is mu J as it is we are getting here, right? First part is mu J as it is we will get. Second part, if we take the mu epsilon dou by dou T term inside to this equation, we will get mu epsilon into, we will take the del out and dou by dou T inside, mu epsilon into del of dou V by dou T. The other term will be what? Mu epsilon with the dou A by dou T. So we will get minus mu epsilon dou square A by dou T square, because already one dou by dou T is there. One dou by dou T will come from here to inside, so it will become dou square A by dou T square. This is our equation. Right, this is our equation, which is equal to what? This is the equation is equal to what? Equation is equal to del cross A. Right, this is from where we started this. We started it from del cross A. So basically mu J minus mu epsilon dou V by dou T minus mu epsilon dou square A by dou T square. That equation is equal to what? Del cross A. Now del cross A, we already used this vector identity before also. That is equal to del of del dot A minus del square A. This is a vector identity. When you are taking the curl of the divergence of a vector, we can also write it as del dot A minus del square A. So we are going to use this vector identity here. How we will use that? This del square A, this thing, if we rearrange it, like this is equal to what? Del dot A minus del square A equal to mu J minus this part. So if we just rearrange it, del square, it will become del square A minus del of del dot A. Means we are, let us say we are multiplying it with minus 1. So we will get this del square A minus del of del dot A. Similarly, the other side is what? This is mu J minus mu epsilon, this term. So that also needs to be multiplied by minus 1. So it will become minus mu J. The negative term here will become positive. So it will become mu epsilon del of dou V by dou T. Similarly, here also the negative term will become positive, plus mu epsilon dou square A by dou T square. This is our del square A minus del of del dot A equation. Right. Now let us take it forward. Okay. Now comes the important assumption, or why this is a valid assumption, or basically we are trying to derive the wave equation here. Here the assumption is that we already defined the curl of vector A. What is the curl of vector A? Del cross A. Del cross A is defined as what? B, the magnetic flux density. Similarly, we just want to define what? The divergence of A. Now you just assume that del dot A equal to minus mu epsilon into dou V by dou T. We will come to afterwards, the next lecture we will come into why we made this assumption that del dot A equal to minus mu epsilon dou V by dou T. Okay, minus mu epsilon dou V by dou T. That is what del dot A is. Okay, that is our assumption. Now, this condition we call as Lorentz condition for potential. This particular condition is called as what? Lorentz condition for potentials. Okay. Now, I just want you to do is this much only. What? Apply this in the equations that we already derived. What are the equations we derived? We derived the first equation we derived is what? Del square V plus dou by dot T of del dot A equal to minus rho V by epsilon. This is the first equation. Second equation is on the last slide. What? Del square A minus del of del dot A equal to minus mu J plus mu epsilon del of dou V by dot T plus mu epsilon dou square A by dot T square. Okay. This is our two equations. I just want you to do this much only. What? This is our assumption. Del dot A equal to minus mu epsilon dou V by dot T. This assumption means in place of del dot A, you have to substitute what? This equation, that del dot A equal to minus mu epsilon dou V by dot T. Okay. Apply that equation into the these two equations. Okay. And apply these equations in these two equations. So all of you take a paper and write this two equation first and apply this assumption. What is the assumption? Del dot A equal to minus mu epsilon dou V by dot T. So apply that, and whatever you get, once you apply that, whatever you derive from that equation is called as wave equation. I want you all to take a paper, write down this equation, and just substitute the value of what? Del dot A. Then the link that's given as a question in Google Classroom. You can upload your answers in that question, which will be considered for today's valuation. Okay, today's evaluation. So just derive this if you have time. After substitution, it will be very nice if you derive the whole wave equation also yourself. We will discuss about the wave equation and its importance in the next lecture. This equation derivation is quite important, so that is why if you like, you can once write down in paper for today's classwork part. The answer this question, that substitute this and write it in a paper, scan it and send it to me in Google Classroom. I will be evaluating that. So after once you are done, you can upload that. So from the next class we will discuss more about the electromagnetic field, basically the time harmonic fields. What is meant by that? Okay, basically time harmonic field means something which is varying periodically with respect to time. So we will see the space and time variation of time of electromagnetic field from the next lecture. Thank you for listening. So answer your question in Google Classroom.